Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll. This is the Q&A video associated with the idea of geometry and topology. Two ideas, I know, I understand. But we're going to get pretty straightforwardly into this Q&A video. It's going to be a combination, as usual, of questions people actually asked and things that I kind of would have liked to say, and I'm going to use this excuse to say them. The first one I'm going to start with is the idea of embedding. So we talked, just to remember, in the geometry and topology video, about, come on now, we talked about two things. The geometry section was about how you intrinsically define the geometry of some space we called a manifold. Okay, a manifold is the kind of thing you can define the geometry of. And the insight of Gauss and Riemann that you could do that, the two interesting things. Number one, you could do it locally. So you could have curvature of some kind of space that could change from point to point. It didn't have to be like a plane or a sphere where the curvature was exactly the same at every point. You could actually characterize locally what the curvature is. And number two, you could make that characterization without thinking about the embedding of the manifold we're talking about in some bigger space. So that raises the question of what do you mean by an embedding of something, okay? So let's get the idea straight first, and then we'll define it a little bit more carefully, a little bit more mathematically. Just think about the circle, S1, the one-dimensional sphere. It can be embedded in the plane, R2. Oops, I could write a better 2 than that. So what we mean by that is, of course, we can have x and y. Okay, so we have our coordinates on the plane, R2, and let's say we have a circle of radius capital R centered on the origin. Okay, so we can draw a circle. Let's see if I can actually make that happen and try to center it in the middle, more or less. There we go. And we're going to say that the radius of this circle is capital R. Okay, so when we this is how math works very often, that we have some idea and we try to make sense of it. It's very much like physics, except we're never comparing our ideas to data, we're just comparing them to other ideas. That's why it's a little bit more abstract sometimes than physics is. So in this case, you can say, well, look, I have the plane, I can just draw the plane right there on the board, and I can draw the circle inside, and it's kind of obvious what I mean. We want to translate that into equations so we can manipulate it. You know, again, this goes back when we talked about space in one of the videos a long time ago, and you talk about extra dimensions of space. Or when you talk about Hilbert space in quantum mechanics, and the number of dimensions of Hilbert space can be enormously large. And we can have extra dimensions of ordinary space that are hidden from our view. And people want to say, well, how do you visualize it, right? And the answer is, you can try, and there's sort of shortcuts to doing your job, but ultimately, it doesn't matter how you can visualize it or not. What you need is a rigorous mathematical description so that you don't need to be able to visualize it anymore. And this is exactly that kind of thing that we're doing here. We have this visualization of drawing a circle in a plane. We want to promote that to some careful mathematical characterization. And then once we have that, we can talk about embedding an 8-dimensional circle in a 20-dimensional space. Completely impossible to visualize, but the equations will guide us. So one way of thinking about the circle embedded in the plane is, well, we have coordinates on the plane, okay? And so we can say where the circle is as a subset of the plane by specifying some condition on the coordinates. So the circle in this case is x squared plus y squared equals r squared. In other words, the circle is a subset of the plane consisting of all of the ordered pairs x comma y such that this is true. In other words, to be a little bit more formal, S1 equals the set of ordered pairs x, y such that x squared plus y squared equals r squared. At least this circle equals that. There's other circles you can put elsewhere. And of course, if we're only interested in the topology rather than the geometry, we can also smush the circle in different ways, but now this is just a particular circle we would like to care about. So this might lead you to believe, and it would be perfectly natural to say, well, the right way of thinking of an embedding of one space in a bigger space is to start with the bigger space and find a subset of it, maybe of some different dimensionality. It turns out that in general that's not the most useful way to do it. In particular, if we want to do geometry inside the embedded space, so inside the circle, we haven't put any coordinates on the circle itself here, right? We just had the coordinates in the plane. We're sort of really taking advantage of the fact that we're living in the plane. And the spirit of geometry, of Riemannian geometry, is that we shouldn't care about the space we're embedded in. We should care about the space that we're intrinsic to, that we're living in. So one thing we can do is put coordinates on the circle by defining an angle theta. Okay, so theta goes from 0 to 2 pi. Let me be very careful about it and write it this way. This square bracket means that we include 0 in our coordinates, and the round parenthesis means we don't include 2 pi. So every number less than 2 pi and greater than or equal to 0 is included here. So theta equals 0 is this point right here. This is theta equals pi over 2. This is theta equals pi. This is theta equals 3/2 pi, and this is almost 2 pi, okay, and 0. So now we know where we are in the circle in terms of theta, and we can relate theta to x and y. And in fact, we can do that. So this is really how a modern mathematician would think of an embedding from S1 into R2 as a map. Remember, mathematicians are constantly thinking of maps between different spaces. So we have the circle by itself with coordinates between 0 and 2 pi. We have R2 by itself with coordinates x and y, and what we want is a map. So whenever you give me a value of theta, I give you a value of x and a value of y. So if you think about it, I want something that says that x equals r when theta equals 0, and then x goes to 0 as theta goes to pi over 2, x goes to minus 1 when theta goes to pi, etc. So if you think about it, what does that do? If we plotted theta and we plot x, what is x doing? And let's put tick marks here for this is 2 pi. So this is pi over 2, and 3 pi over 2. Okay, so what we're looking for is a curve that is equal to 1 at the beginning, goes down to 0, then minus 1, then 0 again, then up to 1 again when we go all the way around the 2 pi. So it looks like this. And now, if this isn't immediately recognizable to you, this is the cosine of theta. And sorry, I said x equals 1, but in fact, what I want is x equals r, okay, when theta equals 0. So this curve is r cosine theta. Whereas y starts out at 0, right? Y equals 0 when theta equals 0. It goes up to capital R, then it goes back down to 0, then it goes to minus R, then it goes back to 0. So y goes like this. And again, that's a very famous curve. This is r times sine of theta. So what we have is an explicit map between the coordinates where other way around, theta, which is a single point on the circle, goes to a point in R2, the ordered pair r cosine theta, comma r sine theta. So that's an example of an embedding. An embedding is a map from the small space, the space being embedded, into the bigger space, the space in which it's embedded. And then once you get that idea, you can do that not just for a circle, but you could do it for two spheres, the whole thing. That you find some coordinates on the small space and you map those coordinates into the coordinates of the bigger space. That's what embedding is. So that's what an embedding is. We want to put it to work. We want to understand, because someone asked, how do you get the metric for a space where you don't know what the embedding is in some bigger space? And, the answer is you just do. That's sort of what it is. But I get why there's a question there, because very often it can be useful to actually define a space in terms of its embedding. Like very often when people say, what do you mean by a circle? There's a topological way of talking about the circle intrinsically, but you could also say the circle is the set of all points in the plane a distance r from the origin. distance capital R that is fixed, right? That defines a circle. So you might think, well, the definition of some space is how it's embedded in a bigger space, and then you can inherit the metric on the smaller space from the metric on the bigger space. So let's see how that actually works. So consider a sphere, a two-dimensional sphere, S2, the two-dimensional surface of a sphere, the conventional thing, embedded in R3. Okay, embedded in three-dimensional space. And this is very helpful because we know a lot, we have some intuition about R3. Here's X, Y, Z. And we can imagine a sphere embedded in this space, okay? And here's a sphere, make it a bit bigger maybe. Yeah, there we go. Okay, good. So this is, oops. Yes, I want to move it. Oh, there we go. So this is a sphere, and so it has an equator, okay? And I'm going to pick out a point on the sphere. There we go. And let's say, again, radius r for our sphere. And again, the whole thing is x squared plus y squared plus z squared equals r squared. That is one way of talking about the definition of this sphere. I want to put coordinates now on the sphere. How do I do that? Well, now what we're gonna do is drop down a line into the xy plane. From whatever point we start at, we're going to go vertically down in the z direction till we hit the xy plane. And that's going to define for us this angle between the x-axis and where we get to, and we're going to call that phi. Okay. Then we're also going to define an angle that starts at the z-axis in the minus direction. So we're going to draw, let's say, a line of longitude here that goes through our point, goes all the way to the south pole. And then the angle from the south pole up here, we're going to call theta. So we have two angles that we can define to tell you where you are on the sphere. Phi goes from 0 to 2 pi, because if you think about it, as you go around the circle, you can go anywhere around the equator. Phi goes from 0 to 2 pi. Just to make it a little bit simpler here, let me just redraw this. Phi is this way, theta is this way, okay? That's the secret. That's what the coordinates are on the sphere. So theta goes from 0 to pi, if you think about it, because inclusive, because 0 is the angle at the south pole, pi is the angle at the north pole, measured in radians, and you don't need to keep going because you've already covered the other half of the sphere just with a different value of phi, okay? So they have different ranges, but these ranges, all told, cover the whole sphere. You will also notice, I was trying to be careful here, phi goes from 0 inclusive to 2 pi exclusive, because 0 and 2 pi are the same. Theta needs to go from 0 to pi including both, because theta equals 0 is the point, namely the south pole. Theta equals pi is the point, the north pole, okay? And so what that means is, for any value of phi, when theta equals 0, you're at the south pole. So there's a sort of not quite smooth map. It's not an invertible map from theta and phi to the south pole. But who cares? And you know how to do it anyway. And the point of me telling you this is that if you know the metric in three-dimensional flat space, which you do, it's flat, then you can figure out what the metric on the sphere is supposed to be. So let me explain what I mean by that. So the metric in three-dimensional space, I mean, you can have whatever metric you want, but there is a conventional metric we often use, which is the flat one. Again, if this is x, y, z, and I have some length, let's imagine the length is very short, so it's ds is the infinitesimal length there, okay? Well, then I can again drop this down and figure out that there is a component in the x direction, dx, a component in the y direction, dy, a component in the z direction going this way, dz, and then the length ds just obeys Pythagoras' theorem generalized to 3 dimensions instead of 2 dimensions. ds squared is dx squared plus dy squared plus dz squared. Okay, that should be believable enough. And what I claim is that, I'm not going to do it, it's a little bit of trigonometry involved here, but if you know how to do this embedding from the two-sphere into three-dimensional space in terms of the cosines and sines, in other words, if you know the one higher dimensional version of this, which is easy enough to do, Then you can actually plug that in to this equation for the metric this is the metric in R3, and you can derive from that a metric just on the sphere, ds squared on the sphere. And what it will end up looking like is r squared d theta squared plus r squared sine squared theta d phi squared. And that's not supposed to be obvious. You're not supposed to be able to guess that. Okay, this is the right answer. This is the metric on what we call the round two-sphere in math. We call it that because two-sphere is often just meant any topological sphere, which we can smush if we want. And so calling it the round two-sphere means a sphere we have not smushed, a sphere that is actually completely geometrically smooth and uniform. And I'm not going to derive this. You can derive it at home if you want to, but I will try to justify it a little bit. Think again, once again, about our sphere. Actually, forget about these axes. Who cares about Euclidean space in which we're embedding it in? We don't need that anymore. Just take the sphere, okay? Here's our sphere. And we're going to have, oops, I don't want to make it bigger. Good. We're going to have an equator. And then we're going to, let's say here is our, I guess we need this one. So here is the x-axis. Okay, that's the one axis we're going to need. Maybe we're going to need the z-axis also. That's x and z. And then we have some point on the sphere, okay, that has coordinates theta and phi as before. What we're going to say is, let's imagine we have a small distance along the sphere between 2 points. Label that ds. That's the length of that small little line interval on the sphere. And we want to express it in terms of the changes of theta and phi. So what we want to do is zoom in on that. So let's take this picture, move it to the side so we can keep it for comparison purposes. Okay. We're going to zoom in on that little thing on the sphere. So we have 2 points of length ds. What we're going to do is, just as before, we're going to sort of draw a line of longitude through the first point. And then we have a line of latitude. Oops, it's supposed to be through the first point. Sorry about that. Let me erase this. Put this up here. Z is up there. And now a line of latitude. Very, very good. So we're comparing the second point to the first point. So this little segment here has a coordinate change d theta. This little segment has a coordinate change d phi. But here's what you notice. The metric, of course the metric is going to be proportional to r squared, because the metric is the distance squared. And as you change the radius of the sphere, all the distances change with r. So the distance squared changes with r squared. So of course there's going to be an r squared. And as theta changes, remember theta is the angle up this way, theta is uniform on the sphere. A change in theta leads to the same physical change in distance, no matter where you are on the sphere, so it's not surprising to see d theta squared. But in phi, that's not the same. In phi, if you're here at the equator, d phi being any size leads to a large change in physical distance, whereas up here, near the pole, the same change in phi, the same change in which line of longitude you're on, changes only a small physical distance, okay? So what we want is to take r squared d phi squared, but multiplied by some function, which is small when theta equals 0, grows to 1 when theta equals pi over 2, and then grows back down to 0 when theta equals pi, because that's the range of theta, okay? So theta is telling us which line of latitude we're on. So let's see if we can find a function like that. Oh yes, we can. If you look at the green line right here, the sine function goes from 0 at theta equals 0 to 1 at theta equals pi over 2, and then down to 0 again. So that's reflecting the fact that a circle is small at theta close to 0, is big, a line of latitude is big at theta equals pi over 2, and then is small again at theta equals pi. So that's why we get r squared sine squared theta d phi squared. So even though I didn't derive it, I think that it makes some physical sense why the metric, the formula for the distance squared, an infinitesimal distance squared in terms of the coordinate changes, has this particular form. The point is, I can literally derive it by starting with this, starting with the formula for the Euclidean three-dimensional thing, plugging in the formulas for what x, y, and z equal as functions of theta and phi, doing a bit of calculus, and this would pop out. If you're familiar with that, then it's very natural to ask, well, what if I don't have any of that? What if you're telling me like space-time, the four-dimensional space-time in which we live, isn't embedded in some bigger space, then how do I know what the metric is, okay? I have a very short answer to this. I'm giving this long-winded explanation just so you know a little bit more about embeddings. But the short answer is you don't know ahead of time what the metric is. That's what you're solving for when you're doing something like general relativity, okay? In general relativity, the game you play is you say, I have some physical situation. You have, let's say, I have matter distributed uniformly through space, but it's allowed to expand or contract, and then you ask, what is the metric corresponding to that situation? And so you try to find a formula for the infinitesimal distance as a function of t time, x, y, and z, okay? And that will be your metric that can describe that physical situation. And you go back and forth. Now you're doing science. Now you're not doing math. You're asking what kind of metric, what functional form of the metric as a function of x, y, z, and t can possibly describe this physical situation. And never during that operation do you need to actually talk about any embedding space outside. So when we get to talk about general relativity, we will see that procedure in action a little bit. Okay. Another question, totally separate question. Remember we talked about the Riemann tensor, and I want to talk just a little bit about different ways of thinking about the Riemann tensor. I told you a way of talking about it, which is not the way that almost anyone would talk to you about it when they initially proposed it, when they initially explained it to you. So what I said was, look, let's say you have some vector, v1, and another vector, v2, and you use that to define a little loop, a little closed loop in space by, they're both infinitesimal vectors, so you sort of infinitesimally follow first down v1, then v2, then backward along v1 again, and then backward along v2. And while you're doing that, you take a third vector, call it v3, and it gets moved around by parallel transport. So knowing what the connection is on whatever manifold you have, that's a rule for what the components of the vector do as you parallel transport them. So you're going to go around a loop, okay? You're going to go around a loop in, let's say, the clockwise direction, this way. And you're going to find at the end that if space is flat, the definition of flat in this case is that v3 comes back to exactly where it started, no matter what v2 and v1 were, and in fact no matter what v3 is. Any vector transformed around any loop comes back to where it started. That means space is flat, at least at that point. But in general, it won't. Okay, so v3 will change from here to here, and so we are able to define another vector, v4. So the Riemann tensor literally is a map from three vectors, v1, v2, v3, from three vectors to a fourth vector, v4, okay? It's an answer to the question, given the vector v1, v2, I go around a loop, carrying with me vector v3, by what does vector v3 change? The answer is vector v4, that's what the Riemann tensor tells you, okay? But this is a little abstract, even though it's a very physical way of sort of drawing the picture, etc. We need to be able to put it to use. So once again, we need a way of sort of quantifying it, a way of actually taking the answer to the question, by what vector does it change, and making it coherent, making it specific, giving you actual numbers or formulas or whatever. And the way we usually do that is coordinates, okay? So we pick not just random vectors, v1 and v2, but we say, like, on our curved manifold, whatever it is, there's some coordinates. I'm going to draw them as squiggly lines just so they're not necessarily Cartesian or polar or whatever, but they're just some coordinates, and call them maybe x is increasing in this direction, y is increasing in that direction, okay? And so at any one point, let's take this point right here, I can say, well, I move a little bit in x, and that defines a vector in the x direction. and then I move a little bit in y, that defines a vector in the y direction, okay? And it's perfectly clear what those vectors are, like they're along these coordinate labels, these lines, okay? So having coordinates defines vectors automatically. And therefore, all these vectors, v1, v2, v3, rather than just saying, give me any vector, I can say, give me the specific vectors at every one point that point along the directions of my coordinate lines. And if I answer the question about the Riemann tensor for those vectors are a basis. It's a vector space. I can express any vectors as a sum of the vectors, as a weighted sum of the vectors here, and that's therefore all I need to do. So typically, people will give you the Riemann tensor by saying, well, I'm going to move along. So let's do it this way. Let's let x mu be the set of coordinates. And let's say the set of all coordinates. Let me just write very vaguely coordinates. So specifically, in space, that would be x, y, z, maybe, or maybe x, r, r theta phi, if we were doing polar coordinates. In space-time, this could be t for time, x, y, z, okay? Or something like that. It doesn't matter, whatever the coordinates are on your manifold. And then there's a vector pointing in the direction of each coordinate. And so then I can think of the Riemann tensor, R, as being specified by a set of numbers, namely the coordinates of the vectors in this coordinate system. So what I need is R equals a set of numbers. I won't write R because R will mean something else in another video soon enough. So let me say Riemann tensor. So this is not Riemann tensor at all. This is just coordinates. Riemann tensor is a set of numbers equal to what the components of these vectors are in this coordinate system. Or in other words, if you do give me v1, v2, v3, this set of numbers converts it into v4, okay? In coordinates x mu. And what that's, I'm going to skip some steps here, but I just want to, this is basically, I'm telling you now something I will tell you exactly again when we talk about general relativity. But this is the kind of thing that hearing more than once doesn't hurt. So the Riemann tensor becomes something which is a collection of numbers which we might write r, lambda, rho, mu, nu. Okay? And what this means is a 4 by 4 by 4 by 4 set of numbers. And those numbers are exactly the components, or what you use to convert the components of v1, v2, v3 into the components of v4. So in this case, I'll give you just a little bit more of details, more than you need, but hopefully it won't actually cause you active harm, okay? So if you let v1 have components, v1 mu, so that's the component of v1 in the time direction, in the space direction, in x direction, y direction, z direction. So that's v1 0, or let me call it v1 t for time, v1 x, v1 y, v1 z, right? 4 components of a 4-dimensional vector in space-time. Likewise, v2 goes v2 mu, and v3 becomes v3 mu. Then the answer to this question, the original Riemann tensor question, what is the map from v1, v2, v3 to v4, is v4 lambda. I can use any Greek letter I want to be the index. It doesn't matter if it's mu or lambda or rho. I could use alpha or beta. It's just an index. It's just a label. v4 equals r lambda rho mu nu. v3 rho v1 mu v2 nu. And just to be clear what this notation is saying, what I'm doing is I am summing over the values of rho mu, and nu. Okay? So what this is saying is I have the vectors. I express the vectors in terms of coordinates. I have a bunch of numbers giving me, characterizing the Riemann tensor, 4 by 4 by 4 by 4 array of numbers, okay? And so I take the components of V3, I take the, rho equals, oops, I'm messing up my plot here. I take rho equals 0, and I take rho equals 0 there, and I multiply those things together, and I add that to the thing I get when rho equals 1, and when rho equals 1, and when rho equals 2, and rho equals 2, and rho equals 3, and rho equals 3. And I do the same thing for mu and v1 and nu and v2, okay? And what I will get is indexed by lambda, which is not summed over on the right-hand side, you'll notice, and it leaves me with the components of v4. So this is an explicit map from the components of 3 vectors to the components of the 4th vector, okay? And immediately from this, you notice some things. If this is something that was followable, here's a fun fact you can derive, that there is a symmetry, in this case an anti-symmetry of the Riemann tensor, r lambda rho mu nu, which is again a collection of numbers, 4 times 4 times 4 times 4 equals 128 different numbers. They're related to each other, though, in different ways. So, for example, r lambda rho mu nu equals r lambda rho nu mu minus. There's a relative minus sign between these two things. Why is that true? Because remember what it meant was, this is v1, this is v2, and we were going around a circle in that direction. So basically switching mu and nu switches the roles of v1 and v2, right? Because that mu is multiplying v1, nu is multiplying v2. So switching, let me put this over here actually, this will be more useful. If the first set of components of the Riemann tensor corresponds to going around clockwise in the loop, the second set of components where we reversed nu and mu corresponds to going around counterclockwise, which is essentially the same information, but in the opposite sense. So it always picks up a minus sign. So this is a symmetry, or in this case, an anti-symmetry of the Riemann tensor. Anyway, the point is, since there was a question about this, but I've used it to babble on a little bit, the conventional way of storing the information in a tensor in general relativity, even though the definition of a tensor is this abstract map thing between vectors, the literal way that you store it is in a set of numbers, a set of functions over all of space-time, okay? So this 4 by 4 by 4 by 4 set of numbers is like a 4 by 4 matrix, a 4 by 4 array, in which every element of the matrix is a 4 by 4 matrix, is not a number, all right? That's why general relativity becomes complicated. That's why life is complicated sometimes. All right. Maybe that was interesting. I don't know. I find it fun. I mean, you might look. The point is, I am not giving you enough information to do these calculations. I have not given you the explicit formula for the Riemann tensor in terms of the metric, for example. But you get the spirit of it. You get what this, that formula for the Riemann tensor you could look up, and it wouldn't be that hard for you to understand. And that is what professionals in general relativity are using. You're not that far away from what the real researchers at the forefront of their field are doing. They have a lot more background knowledge and a lot more practice pushing around the technical symbols, but these are the concepts that they are putting to use. Okay, let's completely change gear here. Let's move to topology a little bit and talk a little bit more about homotopy. Remember, homotopy was a set of concepts, classes, technically speaking, equivalence classes. That looks like DASes, doesn't it? Equivalence classes means, we're going to call two things equivalent if, and then you explain what the relationship is. So these are classes of maps from spheres into some space X. And we call that the nth homotopy group of the space X. So we said, for example, pi 1 of the circle, well, is the set of all the different ways you can map a circle into a circle. And basically, you can either map it all into the same place, or you can wind around once, or you can wind around twice, or you can wind around -1 times, etc. So this turns out to be the integers. It is classified by a winding number, the integers. And indeed, it's not that hard to show. You can go on in your life, grow up, do more homotopy theory, and show that pi n of Sn is always z. If you map a sphere of any number of dimensions into another sphere of the same number of dimensions, you will always get the integers. There will always be a winding number. So people are asking, well, okay, what if I map spheres into spheres of different numbers of dimensions? So let's say I want to calculate pi1 of S2. What is that? So I have a sphere. I'm not going to try to make it pretty anymore. Okay, here's an S2. And I want to map, oops, that's not what I want to do. I want to map a circle into that sphere. Okay, so here's a circle, S1. I want to map it in. Well, what can I do? And I want to fix a base point. So let's fix a base point here, let's say. And let me just draw a particular circle. Let's say that I try to get one that wraps around. Okay, I've wrapped once around. But the point is, these are equivalence classes under smooth deformations. So I'm allowed to, what I'm asking here is, can I deform this particular map into one, let's take a different map, one that just sort of goes around in a little circle, that does not wrap around anything? Well, the answer is that these are exactly topologically equivalent. I can take this yellow one and deform it by just moving upwards in every direction to something that looks like this, and then to something that just wraps. Oops, that was not a very good illustration of what I'm trying to do here. What I'm trying to say is I can pull this up. So let me say that this goes up to something that looks like that, and then I can keep pulling it up, something that looks like that, and I can just pull it over until it just squeezes down to a point. So the point is that there are no non-trivial maps from a circle into a sphere. There's no non-trivial, non-contractible way of mapping a single circle into a two-dimensional sphere. So pi1 of S2 equals 0, equals the trivial group, the group with just one element. Okay. So there you go. And it turns out that it is hard to calculate the homotopy groups of different spheres. The n spheres mapping into n spheres is easy, but n spheres mapping into m spheres is in general very hard. Happily, what you might guess is that if you have pi n of Sm for n less than m, so if the sphere you're mapping in is smaller in dimension than the sphere you're mapping it to, then it's always 0. Then you can always contract down to a point, okay? That's a fun fact. But when n is greater than m, it becomes messy. It becomes a weird, complicated thing. So I'm not going to tell you that. I'm just letting you know that is a weird, complicated thing. One thing that came across several times, and I was a little surprised because I never even thought of it, but I think I realized ex post facto why it was a thing, was the invertibility of the maps that we talked about. So consider pi1 of R2 minus a point. That was an example that we did in some detail. So we have R2, and we have a point here that we remove. Okay, so that's not there. So that's not part of the plane anymore. It's just a point. I've drawn it as a little disk, which is just a point. And we're mapping a sphere with a base point, a circle with a base point into there. And what I drew was things that look like this. Here's my base point, and then I wrap around once. Okay, that's one thing I can do. And there's a directionality to it, like that. But I can also wrap around twice. And that's a different thing. And I can wrap around minus 1 times, etc. So there's a winding number, so pi1 of R2 minus a point is also z, just like for the circle. And people said, well, wait, what about that point right there? That's a point where your circle intersects itself when it is mapping into this thing. And that means it's not invertible. That means if I give you the point in R2 that I've mapped to, I do not uniquely know which point in the circle I've mapped from. This is not an invertible map. And so my answer to that is that's fine. Who cares? There's absolutely no reason why the maps from the circle to the space we're asking about the homotopy groups of should be invertible. Invertibility was never mentioned. Except that I remembered, of course, that invertibility was mentioned when I talk about the definition of what topology is. Topology is the study of homeomorphisms. That is to say, maps between spaces that are invertible, that are one-to-one and invertible maps, smooth maps with a smooth inverse, or continuous, yeah, just continuous maps with a continuous inverse, okay? That's what a homeomorphism is. But this isn't invertible, right? So that's true, but that's not the thing we're talking about. So the thing with the homeomorphism that we're talking about is between different ways of, let's see, think about that light-colored circle that maps around twice. Let me remove that little arrow there, make my life easier. Here's another circle, and that's too dim, sorry. Let's get something else. Here's another circle that maps around twice. Let me get rid of the yellow one also. Oh yeah, look at that, I'm getting good, okay. So, not getting great, but getting good. Here is another circle that wraps around twice. Okay. The homeomorphism I'm talking about is between these two circles, okay? The orange circle and the green circle here. I want to know whether they can be smoothly deformed into each other. I mean, at least that's one question I want to know. What I really want to know is, what are the spaces that R2 minus a point can be smoothly deformed into? That's what would actually be topologically equivalent. What I'm doing when I'm mapping the circle into a space, or a two-sphere into spaces, when I'm calculating homotopy groups of any different numbers of dimensions, I'm figuring out features of the space that are invariant under homeomorphisms from the space to itself, okay? So I'm trying to figure out features of the space that don't change when we deform it. So R2 minus a point turns out, consider the annulus. So the annulus is, I have a region of space in between two circles, okay? So this, let's see if I can do this, yeah. So this region of space right here is the annulus. It does not include the inner circle or the outer circle, it's just the space in between. That annulus is topologically equivalent to R2 minus a point. And what that means is there is no test of topology that you can do to R2 minus a point that gets you a different answer than gets you in the annulus. You can see that if I, for instance, mapped circles into the annulus, if I calculated pi1 with some base point, I would be able to go around the hole in it just like I did with the plane, etc. If I calculate the dimensionality, the annulus is two-dimensional, just like R2 minus a point is, and there is nothing else that would be different, okay? Sadly, topologists are nowhere close to, nor they imagine they ever will, succeed in getting a complete set of characteristics for topological spaces that tell you whether or not they are equivalent. But we know that if there are two topological invariants of a space that differ between two different spaces, then those two spaces are not homeomorphic, are not topologically equivalent. So we know that the annulus, on the basis of homotopy, it could be equivalent to R2 minus a point. In fact, we know it is in this case. But we know it cannot be topologically equivalent to a sphere, because a sphere has trivial pi1 and the annulus has non-trivial pi1. Boom. Since those are different, we know that they can't be the same. So that's a long-winded way, once again, of saying there's nothing whatsoever wrong or weird about the fact that my maps of circles into the spaces I'm looking at cross themselves, that they're not invertible. That's just not something that we really needed to ever care about. Okay, two more quick things. I really should be quicker than I'm being, but these are irresistible topics. I mentioned topological defects. And I didn't say much about them, and it occurs to me that I'm probably not going to get a chance to say much about them for any of these lectures, any of these videos, so why don't I say something a little bit about them right now. So I said that, pi1 is relevant for cosmic strings, pi0 is relevant for what we call domain walls, pi2 for monopoles. I also mentioned textures, but these are the big three. Okay. What I didn't tell you is pi0, pi1, or 2 of what? So it's not of space. Space could be, just R3. It could just be three-dimensional Euclidean space. Even if its geometry is different, its topology could just be R3. So R3 has just one component, so pi 1 of it is just trivial. And it's simply connected, which is a fancy way of saying pi 1 of it is also 0. So pi 0 of it is 0. Pi 1 of it is also 0. You contract every loop, and you can contract every two-sphere also. So it's topologically trivial in all of those ways. But you could get domain walls, strings, or monopoles in three-dimensional space. So what's going on? What's going on is, there's something called let X be the vacuum manifold of a theory. What this means is, we imagine we have some field theory, with, let's say, some scalar fields. Like, forget about complicated things. Just imagine a simple scalar field. In fact, let's imagine one scalar field, phi. Okay? Just a real valued scalar field. And it has a potential, v of phi. And we've looked at potentials that look like, phi squared, simple harmonic oscillator. But let's look a little bit different. Let's imagine that v of phi is minus m squared. Minus m squared phi squared plus lambda phi to the fourth. These are the conventional symbols that are used, okay? So what does that mean? Near 0, the thing that's going to be important is m squared phi squared. So if this is v of phi, that means that near phi equals 0, it's going to be an upside down parabola going like that. But as phi gets bigger and bigger, the lambda phi to the fourth will be more and more important. So it's going to turn over again. And what you're going to get is something that looks like this. Okay? See if we can actually pretty that up a little bit. There. No, clearly we cannot pretty it up effectively. So I'm not going to worry about that. The point is that there is a minimum value for phi, which is either here or here. There are two different minimum values. So if this is the whole theory, you have phi and you have this potential. In the early universe, where the temperature is high, phi is bouncing around because the field is being buffeted by all these other fields, what it means to have a high temperature and everything. And the average value of phi early on at high temperature equals 0. This is fancy notation for average value, expectation value of phi. But later, it's going to be either, if we call this plus little v or minus little v, again, this is the conventional notation, either plus v or minus v. So what's going to happen is the field will start bouncing around near the middle, and then it will fall into one minimum or the other. And the vacuum manifold of the theory is the set of all points for which the energy is minimized. In this case, it's 2 points, okay? Phi equals plus v or phi equals minus v. And what happens is, again, at early times it's near 0. It's going to fall down as the universe cools into plus v or minus v. But in different regions of space, once again, it could fall down differently. So there could be a region where phi becomes plus v, okay? But then around it, there's a region where phi equals, minus v. Not very good handwriting. There we go. So maybe in one place it fell down in one direction, in one place it fell down the other direction. The falling down happens rapidly, and there's the speed of light that says you cannot communicate between different regions that are too far away. So you can't make sure that the field falls down in the same direction everywhere. So in this, it's going to necessarily be the case that there's a boundary between these two regions. And in that boundary, the field is going to have to go from one vacuum to another, and that's going to be a domain wall. That is going to be a region where there is energy because the field has to crawl over this barrier between the two minima. And so whether or not there is a domain wall, I told you, depends on pi 0. So what it means is it depends on pi 0 of the vacuum manifold. So this statement here, that phi late equals plus v or minus v, this set of possibilities, either plus v or minus v, this is the vacuum manifold. This is the space of possible values of the field with minimum energy. It's just 2 points in this case, okay? But pi 0 is the map of just 2 points into the space. So the map of just 2 points with one fixed into a set of 2 points is just 2 points. It's just 2 elements. Pi 0 is not even a group in general. It's just the set of disconnected components, which in this case is non-trivial. There's 2 disconnected components. So pi 0, the vacuum manifold not being 0, is what tells you there can be domain walls. In this theory, there's no cosmic strings or anything like that. There's just 2 points for the vacuum manifold. But let's imagine now you have 2 scalar fields. Call them, imaginatively, phi 1 and phi 2. Okay? And let's imagine our potential, V of phi 1 and phi 2, is minus m squared phi 1 squared plus phi 2 squared, so the generalization of what we had before, plus lambda phi 1 to the 4th plus phi 2 to the 4th. Okay, another generalization of what we had before. So the potential V of phi, I'm not going to draw phi 1 and phi 2, but it's going to look like this. There's going to be a set of points near the bottom where the potential is minimized. Okay, so this is V, this is phi 1, this is phi 2. So this is called a Mexican hat potential. I don't know why it's not called a sombrero potential, but physicists call this a Mexican hat potential. So the vacuum manifold, the set of points for which the energy is minimized, is that circle. The vacuum manifold of this theory is S1, topologically S1. So pi 1, the fundamental group of the vacuum manifold of this theory, is not 0. It is Z. It is the integers. It has a winding number. And what that means is there can be a cosmic string. So if again I draw a space, here's space, okay, imagine that I parameterize where I am in the vacuum manifold, just as I was making coordinates on the circle before. So let me put an angle phi, and I can't call it phi, theta. I'm going to call it theta no matter what. So theta goes around the circle, okay. So I can have, at every point in space, the field once, in early times it's at 0, and it's going to fall down randomly along the circle. So I can parameterize that by drawing little arrows, right? To say, you know, did I fall down there, or there, or there, or whatever. And as a matter of topology, it can happen that these arrows, describing where I am in the vacuum manifold, fall down in a configuration that looks like that. And if I ask how I can smoothly fill that in between, yeah, it's no problem. Smoothly filling it in all the way around, all throughout space. I can fill it in some smooth way until I get very close to the middle, and there has to be a singularity. There has to be a point where I climb out of the vacuum manifold and sit back at the top at phi 1 equals phi 2 equals 0. And that space, that place will have energy because it's at the top of the potential, and that will be the location of a cosmic string. You might say it doesn't look like a string to me, it looks like a point, but I've only drawn 3 dimensions of space. So if I draw, you know, the third dimension, z, oops. So if I, you know, can I deform this? I wonder if I can. Probably not. But if I say there's a third dimension pointing this way, z, then this point that is the cosmic string is going to extend in that z direction, okay? So there's a one-dimensional line through space where the field lives here at the top of its potential, and there's energy there, and that's a cosmic string, and that is because pi 1 of the vacuum manifold is the integers. So in fact, there will be cosmic strings with winding number 2, etc. So that's where the relationship comes from between topology and topological defects. It's not the topology of space that we're talking about, it's the topology of the space of zero energy field configurations that we're talking about. That's what the vacuum manifold is. Okay, one final topic, and honestly I really shouldn't do this, but I'm going to try to do it very, very briefly. And I shouldn't do it just because it's actually kind of subtle and involves calculus in an important way, but it was asked, so I should answer, and it is the topic of cohomology. not cosmology. This is a completely different thing. So there's homology and cohomology, which are two different sets of topological invariants over and above the homotopy that we already talked about. So homotopy is one thing, homology is another thing, cohomology is another thing, and they're all very difficult. In fact, physicists and mathematicians have different attitudes towards these because physicists really like homotopy groups because they keep appearing in situations like this. Cosmic strings are classified by homotopy groups. But to calculate homotopy groups, I mean, pi 1 of S1 is easy, but pi 37 of some complicated symmetry group of something might be really, really hard to calculate, or some other manifold might be very hard to calculate. Whereas these topological invariants, cohomology, and its friend, its dual space homology, are easy to calculate, relatively speaking, but hard to actually put into practice, hard to care about in some way. So mathematicians like them so they can calculate them. So what is cohomology all about? Cohomology is basically, here's the example you should keep in mind. Think about a function and its derivative, okay? Think about the simplest function there is. Think about, here's x, here's f of x equals x, okay? So I can have that function, f of x equals x. I mean, I should have tried to draw it through the center there. Yeah, I can draw it through the center better, I think. There we go, f of x equals x. And I can have its derivative, right? df dx just equals 1. And both of those things exist. There's no complication in saying what the derivative is once you have the function. And you can go back and forth, right? You can say x equals the integral of df dx times dx. In fact, this is called the fundamental theorem of calculus, that you can go back and forth like this. So that's nice and kind of obvious and no big deal. Why are we bothering it? What does that have to do with topology? Okay. Well, your life is a little bit calculus. Life is a little bit more complicated if you live on a topologically non-trivial space. This space on which the function was defined, x, is just the real line. There's nothing topologically that complicated about it. What if we were to do this on a circle rather than on the line? So on a circle, let's think of a circle as theta, but theta just goes from 0 to 2 pi. And then if you go from 0 to 2 pi, you wrap around. So I'm not going to draw the wrapping around, but you can imagine it in your mind, okay? So you can plot f of theta equals theta. You can try to plot it, but what you find is that is not a well-defined function, right? Let me up here, let me do the following thing. Let me convert my derivatives into colors, and then I will plot them. So let me make this the color green. df dx equals the number 1, and I'm going to integrate df dx. And I can plot df dx. It equals 1. It's the derivative of x itself, okay? Now, this is not a well-defined function. F of theta equals theta has different values for theta equals 0 and 2 pi. But the whole point of the circle is you're supposed to identify 0 with 2 pi. So in between 0 and 2 pi, it's perfectly well defined. But if we're sticklers, which mathematicians like to be, then this is just not defined over the whole circle. But we can forget that for the moment, and we can calculate its derivative. What is the derivative of x with respect to theta? Well, that's 1. Just like it used to be, right? Just like it was in the x example. So we can plot the derivative of f, df d theta, equals 1, and that is well defined everywhere on the circle, right? Because df d theta equals 1 at both theta equals 0 and theta equals 2 pi. So somehow we can imagine, so if you started with the function that was just equal to 1, okay, and said, well, I want to define a function x, which is the integral of that function. So in other words, I imagine that that function was df d theta. Oops, I said x, but I meant theta, sorry. So if I said I want to define the integral, just like the fundamental theorem of calculus lets me do, then something goes wrong. So in other words, there are functions which I cannot integrate to get another function. You know, the function that is just 1, if I integrate it, it's going to be this theta function, but that's not well defined. So the fundamental theorem of calculus is failing us in some way, and the reason why it's failing us is ultimately because of the topology of the circle. Okay, so in other words, what we're saying here is you can ask the question, how many functions are there that are or are not integrals of other functions, right? How many functions are there whose integral is well defined is another way of saying it. And I'm not going to go into the details, but that's what cohomology does. Cohomology basically says if you have something that looks like a derivative, can it be globally integrated to get you another function or not? And it turns out, of course, that's a very simple thing, but guess what? There's the second derivative and the third derivative and so forth, and you can do this in various different ways, and you can get spaces of different dimensionalities, and you can talk about the homotopy the cohomology vector space corresponding to different topological spaces, and it turns out to be much easier to calculate. It's another way, in some sense, of finding holes, because that we just noticed that the real line and the circle are different in cohomology, but we already knew that, so it's not a new fact. But there's other spaces for which the ease of calculating cohomology lets us topologically distinguish between the spaces in a much more straightforward way. I could do a much better job of explaining this, but it would take a long time. So I just want to give you a little hint of it, because the reason why it's worth giving you a little hint is homotopy is easy to visualize, once again, right? You map circles or spheres into other spaces, then you deform them. And you might ask, well, shouldn't that capture everything? And the answer is no, it does not capture everything. And so this is yet another kind of tool. You can ask about the equivalence classes of spaces that can or cannot be integrated or differentiated in different ways to form other functions, and that gives you another way of characterizing the topology of a space. So once I've given you two examples, homotopy and cohomology, now you can imagine there's an infinite number of examples, right? Which is probably not practically true, but certainly there are many, many different ways of characterizing the topology of a space. And that's what topologists do for a living. So if you're a young person who wants to become a topologist, you're going to be generalizing things like this for the rest of your life. It'll be a lot more fun than that makes it sound, I promise.